This video is about multiple scattering, which is sometimes a quite substantial contributor to the stray light budget of an optical instrument. However, it requires a lot of effort to simulate it using conventional techniques. Therefore, it is often simply ignored to save time and money. But it is still there. In this video, I will show how easy it is to perform multiple scattering calculations in RayJack ONE. And since it is so easy, I strongly recommend that you always consider multiple scattering in future stray light projects to de-risk your development activities and to avoid bad surprises. Before I talk about multiple scattering, let me quickly show you how surface scattering works in RayJack ONE. Let me start with a new simulation in split mode. Ray splitting means that when a ray hits a surface, secondary rays are produced, typically, say, a reflected ray or scattered rays, and so on. This mode is quite suitable for most analysis projects. Let me create a trivial optical system consisting just of one plane, which I call scatterer, located perpendicular to the z-axis at 0. And here I define the aperture. Now I create a scatter model from a BSDF. For the BSDF, I use a Harvey BSDF, a Harvey model, which I called anodized aluminum. And for the parameters, I take something like 1.5 for the strength, -2 for the slope, 3 degrees for the shoulder. I do not explain these parameters right here, but when I run that script, since the BSDF is not yet assigned to an object, it is here found under unassigned entities. And when I click on it, you see it's a rather sharp angular distribution of scattering. Let me now assign it to the scattering object by setting the scatter property of this object, scatter, and I make it reflecting and assign the BSDF. Now I still need a light source. I just take a simple grid source, which is collimated. Let's call it source. On starting at z equals -1 with a very small radius. Let's use something like that. As the direction, I use the +z direction, and let's use 31 by 31 rays. Very, very simple system. Here I forgot a comma, but now it should work. And now let me trace the system. You see that RayJack ONE creates rays in all directions of the hemisphere. And what's actually happening is it uses so-called flux weighting. So the ray fluxes are multiplied essentially with the BSDF in their direction, so that the rays in backward direction, in this case, have a much stronger flux than in sideward direction. It may be 2 or 3 orders of magnitude different. Now, when instead of ray splitting, I use Monte Carlo ray tracing, then there is always one ray hitting a surface and one ray after interaction. So no secondary rays, and something else is happening. Let me simply run it again. Now there are more rays in directions where the BSDF is high. That is called ray density weighting. The advantage here is that the ray fluxes are almost equal. And even if you have double or triple scattering, multiple scattering, the ray fluxes will be like that. Whereas when you use ray splitting, the ratios of the rays with the strongest and the smallest flux get larger and larger in each scattering event, so that the ray statistics will be rather bad. Now let me turn to multiple scattering. For this end, I prepared a small optical system with the same BSDF as before. And let me simply run it up so that you can see what it looks like. So it's a tube with a wane here and a wane here. And again, collimated light incident. And here we have a small detector that should catch the scattered light. So I assigned the scattering as before. And now I used Monte Carlo with a maximum number of scattering events of 10. Now let me run the simulation, and it takes a little while. And then you see that there's a lot going on here because the rays are multiply scattered, but unfortunately not a single one really has hit the detector. Now I would like to introduce the new idea. It's called use of observation rays. In the code, what you need to do is you have to assign here a target for importance sampling. And for the target, we take simply the detector. And now I have to catch the rays on these targets. I do that with a detector, which is so-called ray collector. I could also compute the irradiance and so on. Let's call it simply RC. And the key point is now that you say register observation rays equals true. And I also forgot here to assign it to the detector. Now I catch the rays, but not the standard rays, but so-called observation rays. You see the meaning soon. Let me also make ray tracing in the script. Non-sequential, I call it RT, assign the viewer that I have used before. And let me trace the result. Now, let's see. Yeah, okay, we already have the result. So here we have the blue rays. These are the rays that are scattered here using this ray density weighting. And when you switch on observation rays, what happens is the following. At each scattering event, let me remove it's a little bit hard to see. We have the rays continuing the scatter, but also there will be a so-called observation ray sent towards the detector. Now, there are lots of scattering events here. There are also lots of observation rays, and the likelihood that many of them hit the detector is high. Radiometrically, this method is completely justified. It's a little bit the same logic as when you're using reverse ray tracing, as I have explained in another video. So this way, with only very few rays, you can get an excellent ray statistics for multiply scattered rays. And even if you have 50 scattering events, it would work nicely fast and within a couple of minutes, and depending on the system, maybe a couple of hours, you will have your ray tracing result.